Also, are we on? We're live already? I think we are. Just about going live on the Zoom, on the streaming. Gunnar, I didn't manage to send out the live streaming link. I don't know whether that's important to do that.
You're muted, Gunnar.
Yeah, that changes every day because YouTube somehow generates these randomly for each event.
If you could send that out, it would be useful.
Yeah, I did send it around, so people should have it.
And Sam, I sent you yesterday's video link.
Yeah, thanks.
Okay, so
after, well, in one of the breaks or something.
Okay, welcome everyone to the 6th day of condensed matter physics in all the cities. Before we start, let me remind you of the etiquette of the meeting. So Sam has put a little comment about this in the chat, but basically we encourage interaction. Zoom is more stable without many videos on, but it's nice to have a few so the speaker gets some feedback. And if you have a question, either type it in the chat and Frank will probably pick that up directly, or raise your hand, in which case I will then interrupt Frank at an opportune moment. And I think that's everything. So our first speaker today is Professor Frank Pollmann of the Technical University of Munich. Frank completed his PhD at the Max Planck Institute in Dresden under the great Peter Fulda, and he followed this with a postdoc in Berkeley, then returned to Dresden to the Max Planck as a group leader before taking up his professorship in Munich. Frank has worked on a variety of problems. He's perhaps best known for his pioneering work with tensor networks, both analytically in order to classify topological phases and in developing new numerical tools to gain insights about various quantum states, such as MBL, the quantum Hall effect, etc. And recently he's turned his hand to using tensor networks on quantum computers, and I'm sure that it'll have a transformative impact in that area. So Frank's been awarded several prizes for his work, including the Walter Schottky Prize of the German Physical Society. And it's a great pleasure to have him speaking today. And without further ado, I'll give the floor to him.
Okay, yeah, first thanks to organizers for inviting me to this great event and for putting everything together and making it work. And thanks to Andrew for the introduction. So yeah, I want to talk today about some different aspects of far out of equilibrium dynamics of systems in which we have certain conservation laws. And the work that I'm presenting has been done together with Tibor Rakowski, who is a student in Munich and is about to graduate, and Kurt from Kaiserlink, who's now in Birmingham. So, and please, during the talk, interrupt me whenever you have questions. I'm happy to have some discussions also throughout the talk. So let me start by basically setting the stage and just discussing a little bit the type of problems that I'm interested in, that I want to think about now. So in particular, what we are interested in is that we want to investigate how or whether kind of closed quantum many-body systems thermalize. So let me just be a bit more concrete about what I have in mind. So we want to prepare a system into some non-equilibrium state, and we want to let it sit for a while, and it evolves at time, and then it will eventually approach some equilibrium state. So classically, we have a very clear picture about how to do this kind of experiment. Now we are interested in closed quantum systems. So the setup that we have in mind for all the things that we are looking at in this talk is the following. So we prepare a particularly simple initial state. So we prepare a pure quantum state where we assume that at time 0, all the local degrees of freedom are in a simple product state, right? So for concreteness, for a spin system, you could think of a state which is a product state where we choose each spin randomly on a Bloch sphere, for example. And this state we evolve now with respect to some non-integrable, so non-fine-tuned and local Hamiltonian. So what's going to happen is that under the Hamiltonian dynamics, the initially unentangled degrees of freedom will become entangled, right? So lots of entanglement is building up in the wave function. However, now coming back to the question of thermalization, well, globally speaking, the system is certainly not going to thermalize because we started from a pure state that has zero entropy, and we end up in a state that has zero entropy. So globally speaking, the system is certainly not thermalizing, and we are not losing any information because it's a unitary evolution of the state. So in order to have a notion of thermalization, what we have in mind is now that we are not looking at the state globally, but instead we are looking at some subsystem. And for example, we could look at a bunch of consecutive spins, right? So, and in order to look at them, what we are doing, we are measuring it with respect to a reduced density matrix for this block. And now we talk about thermalization in the closed quantum system if after sufficiently long times, the reduced density matrix will correspond to some thermal density matrix. And the thermal density matrix is then given by conserved quantities, right? So for example, we might have like energy conservation that dictates basically what the temperature is, or we can also have particle number, etc. So basically what we have, we're looking at that we just have a system which has some potentially very complicated many-body kind of quantum dynamics, but in the end, with respect to local measurements, things will be, in principle, at least quite easy again. So to make it a bit more concrete, what we expect, and this is now shown here for a concrete experiment, like conducted on some cold atom setup, where an initial state, in this case, they prepare some charge density state, like a simple product state is produced and evolved under unitary evolution. And we see that at short times, there's very kind of complicated dynamics, but at the end, after long times, like after the time kind of locally thermalizes, we see that the kind of behavior looks quite much simpler. And in fact, after long times, the dynamic of the system is described by a simple kind of hydrodynamic equations. So here, for example, if we have the charge, if a system in which the charge is conserved, then we would, for example, see that the charge obeys kind of some hydrodynamic relaxation. So, for example, if in a system we would just create a certain charge imbalance, then this would then kind of relax according to these hydrodynamic conservation laws. And the question, like, how can we see this? I mean, this is at the way that I'm putting it here, more like it's a level of a conjecture. So if we actually have weakly coupled systems, we actually can think of interacting like simple kind of quasi-particles, giving us some Boltzmann equations, and then we can derive these hydrodynamic relaxation. We, however, will now be mostly interested in strongly coupled systems and strongly interacting systems, where we generically would not expect that these kind of high energy densities to have a proper quasi-particle picture. So we actually have to solve a very kind of complex quantum many-body system. And then this is exactly what I want to talk about. So I want to start from some microscopic Hamiltonian. This could be some spin Hamiltonian of Heisenberg type, or it could be some Ising Hamiltonian with some terms added, etc. And then I want to look, how do we, like, what can we say about the long-term dynamics of these systems? So, and there are two particular topics I want to focus on in the talk today. So the first is about the entanglement growth following the quantum quench, right? As I mentioned in the motivation, said that, well, we might have some setup where we start from an unentangled product state, and we evolve it, and as we evolve it, the entanglement builds up. And the question is like, how does the entanglement grow in these systems? And here, just to already kind of give the main message, we actually find that in systems with diffusive transport, that so-called Renyi entropies will actually have a diffusive growth, right? So we find that depending on what kind of entropies we look at, they might have a different dynamical behavior. So this is the first part I want to cover, and in the second part will be partly a bit technical, but in the second part, I want to introduce a numerical method that will allow us efficiently to obtain the, for example, the diffusion constant, right? So because a question we might ask is like, you just give me a certain microscopic Hamiltonian, for example, some Heisenberg Hamiltonian, and well, another question like, how can we actually see the hydrodynamic behavior after long times, and for example, extract the diffusion constant for such a model? And here I want to introduce a numerical method that can do exactly that. So let me now start with the first part and discuss the growth of entanglement or entanglement entropies. So we know that there are different ways to measure the amount of entanglement in the wave function, and the probably most common way of measuring entanglement is using the so-called von Neumann entropy. Or when people talk about entanglement entropy, they usually refer to the von Neumann entropy. And in particular, what we do is we take our reduced density matrix and calculate the von Neumann entropy for the reduced density matrix. Right? In this case, it's like rho block is now a reduced density matrix as defined in the previous slides. And it turns out the von Neumann entropy is a theoretically very convenient quantity because it has many nice properties that we like or love as a theorist. However, there's a generalization of the von Neumann entropy to so-called Renyi entropies, which are given by this form. So it's like a prefactor times the logarithm of the trace of the reduced density matrix to the power of alpha. And in fact, the Renyi entropy has a nice limiting case. When alpha goes to 1, it actually is the von Neumann entropy. While generically speaking, the Renyi entropies loses some of the nice properties that the von Neumann entropy has when alpha is not equals to 1, it has a nice property that for certain alpha, like in particular for integer alpha and most easy for integer alpha of equals to 2, it actually can be detected experimentally. So there are different tricks using some replicas, using randomized measurements. So there are different kind of techniques that have been proposed that give access to this quantity. So in cold atom settings and also in ion traps, as shown here on the right hand side, there's now a way to measure S2 experimentally in different setups. And that's quite nice because as a theorist, we really like to make predictions and like to characterize systems in terms of the entanglement, or in terms of different kind of entanglement entropies. And it's nice to kind of directly compare these predictions to experiments. But then the question is like, to which extent these kind of the von Neumann entropies and Renyi entropies have actually the same behavior. And in fact, there are certain cases which is completely not part of this talk, but it's still, I think, quite interesting, is that for certain properties, for example, for the so-called topological entanglement, it doesn't matter whether you look at things von Neumann or if you look at the Renyi entropies. So here I want to focus if we have something similar for these kind of dynamical properties. So let me first talk a little bit about the growth of the entanglement entropy, like here the von Neumann entropy. And there I want to just remind you of some very nice pictures that at least help me to understand quite well to the like how to get basically a picture to see what we expect. And the first picture I want to discuss is a system in which we have a weakly or like an integrable system in which we have quasi-particles. And in these systems, we will expect a linear growth of the entanglement entropy. And the picture, which was probably put forward first by Pasquale Colabrese and John Cardy, is the following. So here we have now the real space in x direction. So we start from a simple unentangled product state, which is not an eigenstate of the Hamiltonian, and we evolve it in time. And the way that we can think about it is that this state that our initial state consists of a finite kind of density of quasi-particles that we have here. So here, for example, I would say that, well, wherever like these kind of light cones emerge, we have now a quasi-particle. And as we evolve the system in time, these quasi-particles spread, and they just spread over these kind of light cone. And the angle, like in this light cone, is given by the velocity of that type of quasi-particle. So while we start in the beginning with a completely unentangled state, so a quasi-particle that's localized here on the left of the cut, right? So we have like a blue region and a red region. So if we have a quasi-particle localized in the blue region, it is perfectly here. So there's no entanglement. But as the system kind of evolves in time, the light and the moment that the light cone crosses the cut between the two regions, then there's a finite probability of the quasi-particle being on the left or being on the right. So which means that then we have some uncertainty to pinpoint where this quasi-particle is. And this is now exactly the entanglement that we build up between the left part and the right part. But now you see, just from this simple picture, that the uncertainty, like the number of quasi-particles that don't really know if they belong to the left or to the right, is increasing linearly as function of time. And thus the entanglement entropy is growing linearly in time. So this is a very nice and intuitive picture to see that generically for integrable systems, we expect a linear growth of the entanglement entropy.
Yeah, Frank, question. Is that true for any dimension? I mean, obviously linear in dimension with t makes sense with a finite speed of light, but volume enclosed will increase with t to the d. So is it clear that S should increase linearly or differently in different dimensions?
Well, I mean, here I make okay, so I mean, at the moment I'm really talking mostly about one-dimensional systems, but this linear growth, and it depends a little bit like how you would do the cut, right? So if you just have a volume and you cut it into like take a cube and just cut into two halves, then so I think I would also expect it to grow linearly, right? Because the number of
I think I can picture it. Thank you.
Good. Okay, so this is now the quasi-particle. But again, like for kind of conceptual simplicity, let us now stick just to 1D, just to have a simple picture in mind. And so then we have this picture for a system with quasi-particles, like in integrable systems. But it turns out, at least numerical, there's lots of numerical data, that this linear growth also holds for systems without quasi-particles, right? And here there are some numerical works I'm showing that this also remains true. So this is as much I want to say about sort of Hamiltonian systems or more physical systems. But more recently, and this is mainly due to some really kind of great pioneering works by Adam Nahum and others, a lot can be learned by not looking at Hamiltonian systems, right? So because previously I made the point in saying that I'm studying local Hamiltonians, but there's a lot of kind of intuition or more simple models we can get by looking at so-called random unitary systems. So what is this? So before actually explaining this, let me just first still stick to the idea of having a local Hamiltonian. So if we have now a local Hamiltonian, for simplicity again in one dimensions, and we want to look at the time evolution with respect to this Hamiltonian, what we can do, and this is like also quite common in numerical simulations, is that we trotterize the Hamiltonian. Right? So basically what we do is we just, instead of having the kind of complete time evolution operator U, we just decompose it into gates that act maybe first on on A bonds. So we just first apply these kind of two-side gates on A bonds, and then we apply it on B bonds. And that concludes now a small time step, delta t. And if delta t is like the error that we make from Baker-Campbell-Hausdorff is of the order delta t squared. So we see that if you just make delta t sufficiently small, this gives us a good way of doing the time evolution. So basically, we can now look at the time evolution exactly in this kind of picture that I drew here. So we start from a state, and now we successively apply these two-side gates, and each of these two-side gates is just given by the Hamiltonian acting on a bond. Good. But generically, it is very difficult to study the time evolution with respect to some many-body Hamiltonian. And in order to mimic it in a model which turns out to be much simpler in many cases, is that we just keep this structure. So we keep this kind of trotterized structure, which is what we would get for doing the time evolution with respect to some Hamiltonian. But now we replace these unitaries by random unitaries, which are just drawn from some Haar measure, right? So we just kind of have now these circuits with kind of very colorful random unitaries. And in principle, we don't have to stick to this kind of checkerboard pattern. We can also just use kind of all sorts of random distributions of these random unitaries. So this is a trick that was recently employed by a number of different people. And it turns out that if we are using these kind of random unitary circuits, which in a certain way mimic the evolution with respect to some Hamiltonian, at least in terms of the locality of those evolutions. And it turns out for these systems, it can actually be rigorously shown that both the von Neumann entropy and also Renyi entropies both grow linearly. So just to summarize, so now I just basically made a lot of, we just looked at these kind of different cases, and we always find that that we would get a linear growth in these systems, like in integrable systems, and also in systems described by these random unitaries. Now let's make kind of refine these random unitaries a little bit. So instead of having these unitaries chosen completely randomly, we can actually put some constraints. So we could say that, well, let us now choose random unitaries, but let us make sure that they have certain conservation laws. So in a spin system, for example, we could now choose these random unitaries in a kind of a block diagonal form, such that the total spin is conserved, right? So we just have one phase, like a random phase here in the up block. We have a random phase only in the down block, but then we have like a 2x2 unitary matrix in the up-down and down-up block. So now we can just take this kind of system and again look at the evolution of a system. And for these systems, if we just build in these conservation laws, we can actually no longer exactly calculate these entropies, but we can still do it numerically. And there are certain tricks that allow us to go to rather large systems by mapping it to some classical partition function that can be solved numerically. And let me now show some data that mostly Tibor obtained for such a random unitary network for which we calculate the second Renyi entropy. And here's what we get. So here is now the second Renyi entropy as function of time. And we do see that at short times, it's approximately growing linearly. But then after sufficiently long times, we see that the entanglement or the Renyi entropy no longer grows linearly, but it grows more something compatible with a diffusive growth. So it grows as the square root of t. And it becomes actually more apparent in the derivative, which becomes kind of diffusive after a sufficiently long time. So what we see here is that if we just do the time evolution with respect to a random unitary network that conserves the particle number, starting from some more or less kind of random product state, we just see after sufficiently long times diffusive instead of a linear growth. but the same idea we can now play with a Hamiltonian, and every Hamiltonian, of course, has a conserved quantity because the energy is conserved. So following this kind of intuition that we got from
Frank, we have a question from Nandini Anchavari. What sets the timescale for the change from linear to diffusive behavior?
Oh, this we can see as some sort of local thermalization time that we need to overcome to see this diffusive growth. So this is now the behavior for random unitaries, and let us now look at a Hamiltonian system. And a Hamiltonian system by default has conservation loss because it conserves the energy. So we will have energy diffusion in this kind of system. And as an example, we are now looking at the Ising Hamiltonian with a longitudinal and a transverse field, which is known to be a rather non-integrable Hamiltonian. And well, now the signatures are less clear as they were for the random unitary circuit, but still we see for the entanglement entropy modulo finite size effects, we see that it has a linear growth, but for the Renyi entropies and for S2 and more clearly for S infinity, we actually see that after sufficiently long times, it is leaning towards a diffusive growth instead of a linear growth of the compared to the entanglement entropy. So, and what is the reason for this, or why do we actually expect this different behavior for the for Neumann entropies versus Renyi entropies? And what turns out to be an important factor are so-called rare states. And the intuition that I want to give is now the following. So let us assume that we have, let us say that we are in, that we start from a state. For example, we have, let us say that we have now a system with a SZ conservation, and we start from a state which would be a product state in X. Then in the Z basis, that state would correspond to a superposition, equate superposition of all possible states in the Z direction. So most of these states would relax fairly quickly because statistically, most of the states have like on a certain stretch, they have SC equals to 0. But there are some rare states where we have like long domains of upspins, right? So we have long, like there are parts in the wave function where where there are long domains where like many spins are pointing up. And those rare states, they will relax very slowly, right? Because these states can only relax until we get we just melt this domain wall, and this domain wall in a system with diffusive transport would actually melt then diffusively. And these kind of rare states then show up, for example, in the entanglement spectrum. So the entanglement spectrum is now the spectrum of the eigenvalues of the reduced density matrix, which are plotted here as function of time. And we see that most of them actually decay fairly quickly, but there are some rare states. And these rare states are now actually the important thing that makes a difference, because if we look at the eigenvalues of the reduced density matrix, these are the values from which we obtain the different entanglement entropies. And the von Neumann entropy is actually sensitive to the mean, while the Renyi entropies are sensitive to like Renyi entropies of larger alpha are sensitive to rare states. It's most clear from the sort of S infinity, where we just take the negative logarithm of the largest eigenvalue of the reduced density matrix, right? So from this intuitive picture, we see that the Renyi entropies with a small index versus with a large index are sensitive to like in a different way sensitive to these rare states. Let me close this part now just briefly by discussing some sort of intuitive or heuristic picture for what I just said. So we can basically first think of the state like the state at a certain time, similar to a path integral as a sum over the different histories of in the SZ basis. And now we can split this part, this state, into one part corresponding to a part where the states have not moved, and another part where the states have moved. And then, as I just discussed in the kind of intuitive picture before, if we have diffusion, only downspins within a distance of O square root of t because of this diffusive growth can spoil this rare region. And from this, we see that the amplitude of this will actually depend on this diffusive growth. And then we can use the so-called Eckart-Young theorem that puts a bounds on the Schmidt values, and the Schmidt values are then bounded from below by this diffusive part. And recall, for the infinite Renyi entropy, the value would just be the negative logarithm of this quantity.
We have another question in the chat.
Yeah, just reading. So there's a question in the chat. Did the difference between von Neumann and Renyi depend on which side of the quantum phase transition you were on? QPT, quantum phase transition?
Yeah, Frank, if I can just ask my question. So in the transverse fieldizing model, depending on whether you are on the domain wall side, with small h versus on the, side where all the spins are aligned, say in the x direction, does this difference between von Neumann and Renyi entropy depend on that?
Well, first of all, I would say that it does not, because the only thing that we require for our argument is to have a diffusive transport, and on both sides of the phase transition, we would have energy conservation. So we would expect on both sides diffusive growth. And moreover, the specific Hamiltonian that we are looking at has a term that explicitly breaks the Z2 symmetry. So this model does not have phase transition. So this model, it would have a phase transition if we would not have this HZ term, but then it actually would be an integrable system. So in the Hamiltonian that we're having here, it necessarily, in order to be non-integrable, it necessarily breaks the Z2 symmetry, and we don't have a distinction between paramagnetic and ferromagnetic.
Okay, yeah, thank you.
Sure. Thank you. Good. Here I just flashed some heuristic argument, which basically is also the argument that I gave with my hands before, namely that there are rare regions which take a time proportional to square root of t to melt. And then the main result that we get from this is that if we have Renyi entropies with an index larger than 1, that these kind of rare events will yield a diffusive growth, and for alpha smaller or equal 1, it will be dominated by the mean, yielding a ballistic growth of the entanglement entropies. Good. So this actually concludes the first part of my talk, and I found it quite surprising, because before we started this project, or before we saw Tibor's data for these random unitary circuits with conservation laws, I would have thought that both entropies grow linearly, but it turns out that there's actually a difference depending on which alpha we choose. Good. Before I start with the second part, maybe there are some questions.
Yes, can I ask a question, please?
Sure.
So you seem to only need energy conservation to do this, so there was no difference between integrable and non-integrable Hamiltonians.
But if we had an but if we had an if we have like if you take like for example the Ising model, then we would actually have ballistic transport of energy.
Okay, so what would happen in that case?
Well, if we would have, if the energy is the only conserved quantity, and we would have a ballistic growth, then we would expect also ballistic growth for Renyi entropies. So just once again, so what we try to do is we just show that if we have diffusive growth, if you have some conserved quantities for which we find diffusive growth, if we have diffusive transport in a system, then we can link the diffusive transport in a system to the diffusive growth of Renyi entropies. Right? And
we also have a question from Masaru Hongo. Please unmute yourself.
Thank you. Does your conclusion for the this diffusive growth of the entropy hold for the both integrable and non-integrable system? Or?
Well, right. I mean, like the moment that we have diffusive transport, it holds. So maybe this picture becomes even more clear. So if like right now, what I discussed is the case of having in principle homogeneous systems that we quench. Maybe this intuition becomes a bit more clear for a system where we have, if we have a system where we don't have, let's say that we have a system where we have an inhomogeneous state. So let us say that we have a system where we just cut the system into two parts. And now let's say that we have SZ conservation, and let's say that everything on the left is in a spin up, and everything down, everything on the right is in a spin down. So if we have this kind of inhomogeneous initial state, so we can ask, how does the entanglement between the left and the right part grow? But now we would see that, well, in the far left and the far right, there is no dynamics because we are in a completely polarized state. The only action that we have in the system, if we just evolve it in time, would be around this domain wall. But the domain wall would melt diffusively. So basically the extent of the domain wall will actually grow proportional to square root of t. But then if we just would like to calculate the entanglement entropy, we would say that, well, only the degrees of freedom within this light cone can get entangled, right? So we can just draw a triangle here. So this would basically be now the entanglement entropy S. It's not very easy to read, but now I just say that, well, the entanglement entropy can at most be as high as this triangle from completely entangling the degrees of freedom that are activated, right? So we see that in this case for this inhomogeneous initial states, that all entropies would grow actually diffusively. And it's just that because of this kind of argument that I gave before of these rare events, it actually shows up also for homogeneous states in the Renyi entropies with a larger index.
Okay, we have a question from Masaki Asakawa.
Okay. Hi. So you mentioned that basically for any Hamiltonian dynamics, the energy is conserved. So yes, you see diffusive behavior in the entanglement entropy. So my question is, what happens in the case of Floquet type dynamics if you change the Hamiltonian periodically in time? Then maybe quasi energy is conserved, but quasi energy is conserved only modulo 2 pi or something. Do we still expect diffusive behavior?
Well, clearly, if we were to have other conserved quantities, right? So for example, like these random unitaries, you can think a little bit like this kind of Floquet system, except that energy is not conserved at all. But if you have then say a Z conservation, then that works. If you have now a Floquet Hamiltonian
without any other conserved quantity,
then I wouldn't see why there would be diffusive transport. I mean, but
so
I haven't thought much.
quasi energy is not good enough.
I think so, but I
Thanks.
haven't thought about this. So
Okay.
this is just a guess that I'm saying that.
Okay. Thanks.
Okay, Joseph Sykes has a question.
Hi, this might be, I apologize if you've just answered this, but my question is say you have a Hamiltonian and it has conserved energy, and then you, for whatever reason, you decide to choose a Hamiltonian with extra conservation properties. Does that affect the rate of diffusion even more? So it doesn't, or will it still be, you know, what you expect even if you just have one conservation?
Well, you can get different diffusion constants, right? So maybe if say this, if you have also spin conservation and the spin diffuses maybe slower than energy, so then yeah, then you just might get a small like qualitatively. I would expect the same picture from what you argued.
Right. Okay. Thank you.
And
Okay.
I think there's a
We have a
question.
question from Navinda Singh, and then we have a couple of questions in the chat. Navinda.
Yeah, so my question is related with the nature of noise. So, what is the autocorrelation function for the noise used when you calculate these entropies, whether it is delta correlated or it's a colored noise, or whether this transition from the ballistic to diffusive transport depends upon the nature of noise. Could you please comment on that?
Well, I'm not 100% sure. I mean, about the noise. I mean, like what we get for these kind of systems overall, like even like for entanglement entropies, we do get this kind of KPZ behavior. We get some corrections to them, but those we haven't considered in what I'm discussing here. And for the autocorrelation functions, I don't know what autocorrelation functions were you thinking
Yeah,
about?
so the thing is that you have done tracing. So there is a system, and then you select a subsystem out of that big system, and the density matrix is for that block. It's the reduced density matrix. So while we do the tracing operation, so all these degrees of freedom, you can say environment and the system. So those degrees of freedom are traced out. And so in doing so, one generally gets the master equation, so quantum master equations. And, so this tracing operation introduces the randomness. Otherwise, the system is deterministic if it is integrable. So my question is, in the reduced density matrix, so you do this tracing operation, and so what sort of so basically, I mean,
this is exactly the entanglement that we measure, right? So that, I mean, we just measure, like in the beginning, we start from a product state where this is a pure state, but then we just get this mixing because of the degrees of freedom within the block get entangled with the rest. Is this what you mean?
So if we do this same procedure, let's say we have a whole system, and then there is no block, but for you write the density matrix for the full system, not tracing over. But then, so whether in that case also you will have similar behavior?
No. This is like in the beginning, I just made the point that because it's a unitary evolution of a system, so
yes,
pure state, so the system always remains in a pure state. It's a closed quantum system that we are considering.
Yeah, so it's always in a pure state.
Say it again.
The system remains always in a.
So this is an important part. So we are looking at unitary time evolution. So there's no coupling to any environment.
So randomness, you are talking about the randomness actually in the model. So I was just wondering where the randomness, what is the origin of that randomness in a unitary evolution?
No, there is no. I mean, sorry, going back. So in this picture,
yes,
we have a pure state evolution. It's just that the unitaries we choose at random. Right. So if you have a Hamiltonian system, then each of these blocks corresponds to a trotterization of the Hamiltonian. But for that I'm presenting here, and also for the one where we have, say, SZ conservation, then the randomness is just it's at this level it's a really artificial system. We don't have any. It's not modeling anything kind of physical. It's just basically, we want to have a system that we can handle and a system that still inherits the locality of some local Hamiltonian.
Okay, thank you. Yeah.
Okay, Frank, there are the two questions in the chat, and also we have Arijit Powell who wishes to ask a question. Arijit, perhaps you can.
Yeah, Frank, hi. The couple of questions. This rare state that you showed in your plot, in the plots of the entanglement spectrum, is it, I mean, is there some correlation? I mean, you mentioned this picture of these domain walls. I would have expected these domain wall states to be sort of low or sort of extremal energy states. Is it possible to tune the initial condition that you get rid of these rare states?
Why would you say that? I mean, you could, I mean, if you have a system where, oopsie, I want to draw again, I'm sorry. If you have a system where everything left of the cuts, or like if you have a region where maybe everything here is in the ground state and everything, let's say let's cut the system into 3 parts, then you have like 1/3 is in the highest excited state.
I mean, I would have thought the highest excited state on the other end of the spectrum is again a sort of a
But you can have a system where, like, let's say that you just put part of it into the lowest you just put part of it in the ground state and part of it in the highest excited state, and then you have now this kind of domain walls, but the total energy of the state is at 0, right? So the total energy of the state can be 0.
I see. Yeah. Okay. So you're saying, but that would depend how. Okay. That'll be a rare state. Okay.
So this would be the type of rare states that we have in mind, because now, if you have this state, then we would have energy diffusion to basically like around kind of domain walls. Yes.
So they'll still be at 0 energy. And the second question I had, can you say a bit about the mapping of the trotterized problem to the random circuit? I mean, I would have, in a slightly different, maybe physical picture I have in mind is, as you evolve in time, you're producing more and more non-local entanglement. While in the unitary circuit, I mean, even at late times, entanglement is sort of produced locally. I mean, somehow at later times when the state is quite entangled, some local operation may actually produce quite a multipartite entanglement, because the state at that stage is actually quite entangled. So, but the unitary circuit, maybe that picture is not correct. So where would that be?
But I don't see the big difference, because in both cases we would say that, well, let's say that we start from an initially unentangled state, and in both cases each of these gates would add entanglement until we just reach the typical state and where it will just saturate at something. So just the relation, I mean, like this random unitary circuit has it basically inherits this local structure from a Hamiltonian, but it has kind of basically no conservation laws, right? It just has the
I see.
But the important part is that the local structure stays, and as we can see here, we have, for example, this kind of light cone, right? So degrees of freedom within this light cone that get entangled, and stuff outside not. And this is akin to what we would get also from the Hamiltonian evolution.
Okay, thanks.
Good. So so there are a few questions on the chat, which I maybe read, and then I probably move on to the second part. So there's a question about, I would have expected the imposing of U1 in absence of energy condensation and randomization is less effectively thermalized, but your example shows otherwise. I mean, the U1 quantity, I mean, it would, like, if you just compare a system without any conservation laws, which I haven't, and you just impose a U1 conservation laws, then it actually would indeed grow slower. But the absence of energy conservation, yeah, I'm sorry, I would.
Sorry, I suppose in random unitary circuits you don't have energy conservation, right?
That's right, yeah.
So
well, but the thing is, sorry to interrupt, but that in like what we are showing here, like here we have now like what we are looking is a random unitary that has a U1 conserved quantity, so but no energy. But then we have the other Hamiltonian system which doesn't have a U1, like it doesn't have a Z conservation, but it has energy conservation. But yeah. And also, I mean, it's not so obvious how to compare the time scales, right? Like for the random unitaries, for example, we just measure the time in terms of the Trotter gates. Here we measure the times in J. So it's not so easy to compare these models.
So it becomes numbers, but the exponents will not change, T and root T.
The exponent, right? The exponents for having diffusive or ballistic growth of the entanglement.
Yes.
And they are quality, like in this respect, they are the same. And then how does the crossover from ballistic to diffusive growth compare between the systems with global conserved quantities and the system with only? Well, this question I don't understand, because in both systems we have global and conserved quantities, and one is in one system we conserve the total as Z, and the other system we conserve the total energy. Another question by Sam. Another question, these discussions of entanglement growth tend always to be based on real space, which is perfectly natural. The product state in the beginning in real space and the system cut to define the reduced system in real space. But one can also think of problems in other bases, for example, K-space. Well, but in K-space it's a little bit problematic in such a way that so if we take, for example, an interacting Hamiltonian, like if we just take some Hubbard type Hamiltonian in K-space, then the coupling in K-space becomes highly non-local. I mean, we can of course think of this, we can think of the growth of the entanglement in momentum space, but then we just losing the locality of the Hamiltonian. So, but still, I mean, it would be an interesting question to see how the entanglement grows in these systems, but I haven't thought of this.
Okay, yeah, just the question is based that most things we think of in physics are sort of basis independent. And maybe that is a very key point, that Hamiltonians we write down tend to be local in real space, but not so local in other bases. And maybe this is the key point, that if you find a basis where it's local, then you can expect this, whereas other bases might not. But
yeah, that's exactly correct. This is exactly correct. So if we just, like, what I'm saying is universal as long as you would only allow for local basis change.
Okay, thanks. That's quite useful.
And then what would you expect if the Hamiltonian use is time dependent? Right, I mean, then we're just going back to a system that no longer conserves energy. And as Masaki asked about these Floquet systems, so then we would not conserve energy, but only conserve energy, for example, modulo. Like we would only just conserve the kind of quasi energies. Or if we just kind of don't periodically, if you don't have a periodic drive, but a random drive, then we're just going exactly back to what I was showing for the random unitary circuits.
But if you do it adiabatically, right, you stay in the ground state. So you can have a Hamiltonian that is time dependent, and then you apply some adiabatic evolution so that your Hamiltonian, although, you know, so then you would still remain in the ground state, and would the energy not then be still conserved?
Oh, watch out. I mean, what we are looking at is not, I mean, that's like going back to the title of my talk, it's like we're just looking really at systems far out of equilibrium. We are very far away from the ground state. And if we think of the many-body spectrum, there's no, except we're doing something exponentially slowly in the system size, then there's no notion of adiabaticity here.
Okay, thank you.
Good. Maybe I will just go into the second part, and
I think you will have extra time in the second part. You've taken a lot of questions, so you feel free to take your talk a little bit into the questions and as necessary.
oh, then how much time do you give me? I mean, then I'll just know roughly how.
I suspect we've had 10 minutes of questions or so. So you may overrun by between 10 and 15 minutes, and then we'll leave the remaining 15.
Okay, so I have 15 minutes left then. Good. So let me now really kind of change gears a little bit, because what I did in the first part is that I just more kind of conceptually talked about the growth of different entropies. In the second part, I actually want to talk about some kind of practical considerations about how can we, for a given microscopic Hamiltonian, extract, for example, the diffusion constant, right? So that's like the question. Let's say someone gives me a Hamiltonian and asks me that, well, what do you expect to be the diffusion constant for spin transport, right? So this would be the question that we are now interested in. Well, I mean, the question is then how to do this numerically, and numerically we are generically in big trouble when we want to study quantum many-body problems. Just to put some crazy numbers here, right? So even with the kind of the biggest computers on the world, if we want to study part of equilibrium dynamics, we are certainly there's a hard wall around 40 or so spins, and then all the supercomputers would break down. Good. So basically, the short version of this is that if we want to do something using exact diagonalization by really creating the full many-body Hilbert space, we are just bounded by this exponential growth with system size. Well, then there are kind of smarter techniques using so-called matrix product states that you already heard a lot about in other talks. They give a very efficient way to compress certain quantum states. And then we are no longer bounded by the system size. So we can just write down a matrix product state easily for hundreds of spins. But still comes at a price, because if we now look at our quench experiments, then we will actually find that the complexity will grow exponentially in time, right? So we just trade exponentials. But then coming back to this kind of more intuitive picture that I want to draw here, so we could then basically say that, well, let us now have in mind this sort of matrix product state picture, and say that we start from a product state, like just a simple product state in the language of matrix product state. That means that the bond dimension is 1. So we have really little information. But then as we just quench a system, we find that the number of bits, or equivalently the bond dimension in our MPS, will grow exponentially. So this is kind of coming from the left-hand side. But then at least we conjectured that after sufficiently long times, that the system is described by very few variables, right? So in the end, all we need to know is maybe the temperature for our ensemble. So at the end, at long times, we would actually expect that the system becomes very easy again. But there's then sort of this exponential wall that gives us a hard time. The question is like, is there some smart way to truncate the information without sacrificing kind of crucial information that we need for studying the evolution of a system? Well, what I just said in words, one can also make a little bit more concrete by, for example, kind of doing the time evolution of a system and cutting out a reduced density matrix. This rho is this rho block that I just gave. And here I'm showing some actual numerical data about the kind of bits we need for representing this rho block. And we see indeed it goes up and then it goes down again, and following this intuition that I gave. So now, obviously, this is kind of a very interesting question, and there's a lot of work done on this, following different approaches that I'm not having time to talk about. Actually, some also by the chairman of the session. So let me now first discuss one attempt that we and also others made, which has a very simple idea. So we just start from our kind of matrix product state representation, as I just discussed, where we know the initial states can be represented well. And then instead of following the exact evolution, we are just following the evolution projected into this manifold of matrix product states. And then we will find that in the beginning, this evolution will be exact, but at some point we're going to have some approximated evolution. And using these kind of time-dependent variational principle, we actually guaranteed that the system will conserve energy and other conserved quantities. And one maybe unjustified hope would be that if we just follow this through, that the results that we get might be reasonable. And we tried this out for pure states, but a maybe more general approach was actually proposed by the chairman to actually do this in a thermal field purification formalism. But let me just show flash quickly the results that we got for this time-dependent variational principle, which first got us really excited. I mean, the only thing that I want to show here for the excitement is that we just using this time-dependent variational principle and try to extract the time-dependent, diffusion constant from the mean square displacement. And we see that, well, at short times where it is exact, we see that this grows linear with some diffusion constant. And we see that even after long times, it follows the same trend independent of the level of the approximation. And that made us very hopeful that this magically works. But turned out, if we just switch to another model, that it stopped working. And we still don't fully understand how the magic is lost. But let me not spend more time on this. Let me just now talk about some new approach that we worked about. And the new approach is that we actually introducing an artificial dissipation that leads to a decay of the entanglement in a slightly different way, as a different meaning of what I used before. And that turns out allows us to capture the dynamics to very long times. And the basic ideas go a bit back to some well-known ideas by Murray and Swansea on this memory matrix formalism. But let me just be a bit brief and just kind of outline the ideas. So what we want is we want to calculate, for example, these kind of time-dependent correlation functions, and we want to limit ourselves to infinite temperature expectation values, right? So this is what we want to calculate. And what we are doing now, instead of evolving the state, what we are doing is we are just now want to do it in terms of the Heisenberg evolution. So we want to evolve operators. What we can do for states, like using matrix product states, we can also do for operators and represent the operators in terms of so-called matrix product operators. And we can work with them, but we are still facing the same problem, namely the complexity of those operators in the Heisenberg picture will again grow exponentially in time. So it's just a different way of putting it, and we're just running into the same problem. But here we have now a different handle to get to lose information, and this is by introducing now at this level dissipation on the operator evolution, and I want to motivate a little bit how this works. So, and this goes back, like the kind of intuition goes back to something that we used a lot for studying these random unitary circuits, and this goes back to thinking of operators being expanded in terms of Pauli strings. Right? So if you have now a system, if you have now some operator, we can, acting on our spin chain of L sites, we can always write this operator as a superposition of Pauli strings of length L. Pauli strings of this time, so this is Pauli Z, Pauli X, and the identity, etc. So now we introduce a dissipator of the following form. So we have a dissipator that acts as a super operator acting on our operators, and if the length of the Pauli string is smaller than some L star, it's doing nothing, right? So the length of the Pauli string is just the number of non-trivial Paulis that we have, right? So here, the one that we see here, we have like 1, 2, 3, 4, 5 non-trivial Paulis and 3 trivial ones. So here LS would be 5, assuming that there's only ones on the left and on the right. So simple Pauli strings with few non-trivial Paulis are not touched, and the ones that are more complex are actually damped with this factor. So, and this L star we choose in such a way that it's longer than the conserved quantities considered. So, because if this is the case, then the application of this dissipator preserves this this quantity, right? So, for example, if we want to measure SZ, then we only need to then we can just get rid of everything smaller than L star equals to 1. And if we have like a two-side Hamiltonian and we want to look at energy conservation, then L star has to be at least M2. So, and we have now a handle, and which is the dissipation strength, right? So we know that if if gamma goes to 0, then we're actually getting the exact evolution. So, and now the intuitive picture, and this is now similar to this kind of Moritz-Zwanzig, or motivated by this Moritz-Zwanzig memory matrix formalism, that we just distinguish between fast and slow degrees of freedom. So operators that grow very quickly, they are then damped. But on very general grounds, we assume that the backflow from long to slow, from long to short operators is actually kind of rather rare. And then this has been similar used before, but in this Zwanzig-Mori formalism, it's not so obvious how to kind of bring it into an kind of a simple to apply form. So then, having this in mind, we actually now could say that, well, now we have an algorithm. So we just first do a simple time evolution as we know it from matrix product state formalism, for example, the time evolving block decimation. And then after a certain time, we then apply this dissipator that would remove states, would remove information, and thus it will remove the entanglement entropy. And this is exactly what's happening. So here we plot now the entanglement entropy, and this is now the operator entanglement entropy, basically a measure of how complex our operators are as function of time. And we see that it shoots up in the beginning, and then once the dissipation kicks in, it's actually reduced to kind of smaller sizes. And as long as we have a finite gamma, we never get into the trouble that we cannot represent the wave function. So all the wave functions, all the operators can be represented well in terms of these kind of in matrix product state formalism. So now we can put it at a test, and we see that, and this is, I think, what I find quite nicely on the right hand side. So we just take a model. In this case is a Ising model in a tilted field, and we just compare to exact diagonalization. So the blue dotted line is from our dissipation-assisted operator evolution method, and it shows this diffusive behavior after sufficiently long times. And we see that asymptotically, the finite size calculations converge to it. So this is kind of quite plausible that this is actually giving us the kind of correct results. And now we can make this a bit more systematically. We could say that, well, now we take a Hamiltonian, and we just extract now the diffusion constant. And what we can do now is we have now this handle. So we can, on the one hand, choose our L star, and we can make our gamma smaller, and then extrapolate the gamma equals to 0 limit. And we see that here the different L stars give approximately the same kind of small, or like gamma equals to 0 limit. And this is the way how we can now determine the diffusion constants for these different systems. And we can also compare it to like other models. So previously I showed the Ising model. This is now for XX ladder, where where there's some numerical results to compare to from some large-scale exact diagonalizations, and indeed our algorithm converges to similar data. So this, for example, is a case where this our previous approach using this time-dependent variational principle failed. So it gave like it showed diffusion after long times, but it converged to the wrong diffusion constant. And here, like all the models that we've looked at, it seems that this dissipation-assisted operator evolution actually gets the right diffusion constant in the limit of small gamma. Good. Let me then conclude. So yeah, in the first part, I discussed the entanglement growth in systems with diffusive transport, and we found a difference between, in particular, kind of for Neumann and Renyi entropies with a larger Renyi index. And the second part, well, I rushed a little bit through it, but the main message is that we believe to have found, I think, a very useful method that allows us to extract diffusion constants from microscopic Hamiltonians, right? So that we just have a given microscopic Hamiltonian, and that we can efficiently simulate the long time evolution, at least so far, for infinite temperatures, and extract the diffusion constants. So let me then stop, and again thank Tibor and Kurt for this great collaborations. I mean, it's really them who did most of the work of what I presented. And let me thank you for your attention and all the questions that I already got. And happy to take more.
Great. Let's unmute ourselves and thank Frank in the usual way. Okay, and the floor is open to questions. Okay, Masaki Osakawa, please.
So maybe I missed your explanation, but in one of the slides, I think you showed this on the second part, this dissipation-assisted one. Yeah, this figure,
yeah.
The previous one. So not this one, but with this, you represented this dissipator as kind of MPO or something.
This one here.
Is that so? Okay. So you define the dissipator as some suppression of Pauli string with some length larger than some threshold, and I thought this requires some operator acting on multiple spins. But in one picture, you showed this dissipator as some MPO-like operator consisting of some operator acting on single site. Maybe I misunderstood.
Okay, no, this guy we can represent as in this form. Is this what you mean?
Oh, okay. So it's so it's MPO. So it's
right. And this is, I mean, I didn't think
correlated
because I didn't make it explicit, but
okay.
We can represent that guy with a pretty simple MPO of basically of a dimension of L star plus 1, because what we do is we just start at 0. So the way that you can think about it is like a counter, right? We just put the counter in state 0.
Okay.
And whenever on the way we encounter a non-trivial Pauli, we actually just step up with the counter.
Oh,
right?
I see. Okay.
So then we just go to 1 once we encounter a non-trivial one, and we just still always kind of multiply the wave function with the 1 as long as we are counting up. But once we reach the threshold of L star, we then start applying
I see.
Some damping factor to the wave function.
I see. So interesting. Yeah, thanks.
Great. Frank, I'm going to allow myself a question, if I may. So essentially, you've mapped your open system dynamic, your closed system dynamics to something that's reminiscent of an open system dynamics because you have dissipation, but you nevertheless conserve energy in your dynamics still, even with your dissipator. So
yeah, because
could one write down an imblad for this?
Yeah, well, we have thought about a little bit about this, but there is no, and that would be a very weird thin blood operator, because we are doing this dissipation on the kind of super operator level, right? So it's basically maybe it's most obvious from this plot here, right? So what we are doing is we're just doing the evolution, the first bit here is actually just the linear. Sorry, this is just unitary time evolution, and then we just apply this operator. But this is now some non-Hermitian operator that we apply to the wave function.
Mm-hmm.
But I don't think that there's a proper physical way of doing this.
One might think, for example, of describing a bath that's many copies of your system,
mm-hmm.
but in thermal equilibrium or something, would have this property of conserving the energy and so on. But still, it might be quite different from what you have.
Right. No, but this is an interesting way to think, but we haven't worked out anything in this direction.
Okay, thanks.
So
I see White is on the line and has a question.
Mm-hmm.
So Frank, can you say a little bit about the implementation of the super operator to apply the dissipation?
Sure. Right. So this guy here, I just briefly said, so basically what we do is we just have an MPO where we start on the left with a vector 1, 0, 0, right? And now let us say that we just have a polystring where we have a bunch of something like this. And now we just kind of start on the left and we just go over, if we just reach now this state, we stay in this 0, 0, 0, 1 state, and also like here, but now we encounter the first non-trivial polystring. It could be an X or Y or Z, and what's happening then is that, well, we just step up. And the moment that we then encountered more states, then actually we will start at some point, once we reach to the top, then we start multiplying some number, like some gamma to some power, like then we just multiply it with some 1 minus gamma, such that then the amplitude of the wave function will be diminished, and then at the end we just multiply again with a 1, 1, 1. And this will give us then the amplitude.
So it sounds like you can implement sort of a matrix product super operator to do this?
That's correct. That's correct.
Yeah.
So this is the matrix product super operator that we apply on. So this MPO is a super operator MPO. Yes.
Great.
That's right. Yeah. Mm-hmm.
Okay, we have a question. We did have a question. Someone had their hand raised and it's disappeared. I think it was Jorge. Jorge, did you still wish to ask your question?
Well, thank you for the very interesting talk. I'm a bit embarrassed because this is a question I should have asked like on slide number 2 or something like that.
Okay.
But I was just wondering, in terms of understanding the significance of the question you're addressing,
mm-hmm.
Could you say something about what happens in the classical case? So what happens to Renyi entropy if you have a longitudinal field Ising model? I realize this question probably has a trivial answer, but.
Okay, but then we have to think a little bit. So you say that we are doing, so now what I'm looking at is a unitary time evolution, and I look at the evolution of the Renyi entropies calculated for the block. And now you're saying that, well, let us now do some symplectic evolution for a classical system and study how the entropy of a state is changing. Is this what you basically mean?
Yeah, I'm just thinking some of these models you can tune from classical to quantum. Say you have the transverse field Ising model and you start moving the magnetic field, tilting it. Eventually you go to a classical case, and it seems to me like these things, you cannot even define them for a classical system. And I don't know how to think about that.
No, I agree. This is also what I have trouble with at this moment. I mean, because if I literally go to the classic limit, like let's say that I just do what you said. So if I just take the Ising model, I start from an Z product state and I tilt my field to the Z direction, then of course there's no dynamics, and then this would just come to a halt, right? So then it would not grow at all. But it might be that there are other ways to find some classical analogs. I mean, I can't give a satisfactory answer to this now. I mean, like I would have to think a little bit how to define the analog in terms of classical.
Okay, so thank you. I thought it was a trivial question, but it looks like it isn't. So I'm glad I asked. Thank you.
Okay, so Sam Carr has been asking me to slot him in when there's time.
Yeah, just it's going back to mostly the first part of your talk again.
Mm-hmm.
But the question really is, have you thought about quantum impurity models at all? Because these aren't diffusive systems by any means. What I mean is something which is ballistic except for a single impurity, but that means it's not really ballistic the whole way, particularly if you put your cut at the impurity. And I mean, these can be integrable or not integrable or questionably integrable in many circumstances. And maybe this can give some insight into that.
Right, no, this is a very interesting question, and the short answer would be that I have not thought of impurity models in this context.
Okay,
this is the short answer to it. I mean, if there's something special.
Okay, any guesses, or you just really don't know?
Well, I mean, it depends on the setup. So if you have an impurity model with energy conservation, I mean, then I would think that the same. I mean, then I'm not sure how that would be different from what we have seen.
Yeah, okay, maybe. But the question is, it's got energy conservation, but maybe then take one which is integrable, so it's got a whole bunch of other conservation laws as well. And then the question is, does this act like a diffusive thing where the Renyi entropy is growing diffusively, or does it act like a ballistic one where all entropies are growing linearly?
But again, I mean, I think that I would just link it directly to transport. If you have a system where you have now, if you have your system and you just can identify some diffusive transport, then I would say that, okay, well, in that case, we would expect the Renyi entropies being proportional to that diffusion.
Yeah, okay, but I mean, this is more things that would be given by at least a Landauer formula for a quasi-steady state, perhaps, which is not diffusive, but it's certainly not ballistic either. That's where my question is.
This actually, one sort of related thing, I mean, in a different work, what we have been looking at is transport in systems with higher moment conservation. Like if you have a system where maybe not only the charge, but also the associated dipole is conserved. In those systems, we find some anomalous diffusion, which would go as the time to the power of 1/4. So in one conjecture would be that in these systems, we would actually find that the Renyi entropies would also show this growth, but we haven't checked this yet. But this would be right. So because we just directly, like with this argument, we just directly link the growth of these Renyi entropies to transport in the system, and the conjecture would be that it would also show these kind of anomalous diffusion constants.
Okay, thanks.
We have a question from Piers Coleman.
Yeah, Frank, thank you for a lovely talk. I'm not entirely sure I understood your super operator method for using dissipation, but let me ask you this question. Supposing I wanted to extend it to 2 or 3 dimensions, would it require a higher dimensional tensor network approach, or could you still do it using matrix product states?
Okay, but the answer is that we can, in principle, still use matrix product states. I mean, this also, I think, Miles briefly commented on it, that matrix product states are indeed very powerful. That at the moment, some of the, like at least for 2D, some of the kind of best numerics has been done, for example, by Stephen White, using DMRG for 2D, right? So it can be applied to higher dimensional systems. Mm-hmm. It's just that then it would scale differently. So basically, if we just make the system like now so the DMRG is a one-dimensional method. So in one dimension, we can make the system as large as we want to. But for two-dimensional systems, then it would grow exponentially with the linear dimension. Mm-hmm. So the answer would be that in principle, yes, we can just apply the same technique as I just introduced it with suboperators to higher dimensions, but then the scaling would not be favorable. But in principle, we have started thinking a little bit about this, that the same ideas apply to 2D tensor networks, of course, but then we are dealing with a different class of complexity when it comes to implementing it.
I mean, it would be wonderful if we had a tool for calculating diffusion constants for specific models in 2 dimensions. This is
I couldn't agree more, but I hope, I would be thrilled to have it, but we actually started thinking this direction one thought that I had was to combine this with so-called isometric tensor networks that we had been thinking about recently to do actually time evolution higher dimensions, but it's also getting technically quite challenging, so it will take a while.
Okay, thank you very much.
Okay, we have a question in the chat, Frank, and then a question from Gunnar Mahler after that.
Okay, so maybe I'll read the question from the chat. In the second method, is the second method useful for other operators of interest or mainly for looking at diffusion of conserved quantities? Okay, this is a good question. We haven't explored this. I mean, in principle, we're just doing this operator evolution, and then we can just measure whatever we are interested in. But yes, in principle, we can extract other quantities as well. It's just that we haven't explored it yet.
Okay, Gunnar, perhaps you can ask your...
Yes, thanks, Frank, for the great talk. Just having this tensor network on the screen, I wondered about some of the technical aspects of representing the density matrix in this purified representation. So usually it's very useful to put the MPS into kind of canonical form. So is that a concept that still exists for these density matrices, or is it useful actually when you set up this algorithm, or is it just not relevant here?
Oh no, literally when we do this, where is it? When we do this here, like this identification, we just in principle forget about during the evolution, we basically forget about the system being an operator. So we just reuse codes that we previously used for evolving states, except that we doubled the local Hilbert space dimension. So we still use the canonical form and all that for this time evolving block decimation algorithm.
I see. So then you can just calculate expectations of local operators, essentially constructing the environment to something trivial still.
Exactly. So the same thing applies. It's like basically with this step here, like once you kind of did this step, you can just recycle all your old codes. There's nothing that you need to redevelop. But this is not we came up with this. This is has been done by many people before. To just use this kind of mapping for evolving operators.
Okay, great. Thank you.
Okay, if there are no further questions, and I don't see any, we should again, please. Thank you for great talk. Are you going to be here for the student discussion later on?
Sure. This was starting at, I will be there. Yeah. Mm-hmm.
You'll be there. Okay, great. So predominantly that's younger students, but any older students amongst us who wish to go can come along and ask Frank our further questions then. I think the plan now in previous days is probably to go into breakout rooms and then to return just before 4 o'clock in time for the next talk.
Okay. I just like everyone to turn on their videos. We'll take another screenshot just for fun to have a look at the cast of characters. Turn on your videos. We'll just for fun. Come on, turn them on.
Apologies, my internet crashed.
Yeah, I will take it.
Piers, is now the time to go into breakout rooms?
Hang on, just a second. Picture of everyone. Okay, thank you. Do one more. Smile, please. Hang on. One more. Sorry, I've got some.